In this video, we're going to go over how to find the relative atomic mass considering multiple isotopes using data from a mass spec. So in this graph, you can see the mass charge ratio along the bottom. So the bar over mass 204 would indicate the abundance of the 204 isotope, whereas the bar over the 206 would indicate the abundance of the isotope with the mass of 206, and so on. So I see at the bottom here of the graph, there are 4 different isotopes of this atom. So the first mass is 204, the next mass 206, then 207, and also 208. So you do have to look at the bottom of the graph to figure out what your isotope masses are. Then we're going to look at the abundance of the isotopes. So the abundance will be the numbers at the top of the graph. So for the 204 isotope, the relative abundance is 0.2. Then for 206, you've got 2.4. Then for the 207, it is 2.2. And then for the 208 mass, we see the highest abundance of 5.2. The key part about these numbers is that it is all relative. So we need to figure out how much total mass we might have if this is just the ratio of how much isotope compared to each other. So the easiest way to do this is to find something called the percent relative abundance. So these would be the parts. We have to add them up to figure out what the whole would be. So if I, in my calculator, type 2 plus 2.4 plus 2.2 plus 5.2, I get a total mass, oh I keyed something wrong there, it should be 10.0 grams total. So if these are the ratios, if these are the parts, this would be the whole. So now I want to go over how to find the percent relative abundance, how to go from the second column to the third column here. So let's do the first one for the 204 mass. We're going to take the part that we know is 204, which is 0.2, and we're going to divide it by the total mass that we came up with, which is 10. It is a percentage, so of course you're going to multiply it by 100, and that will give us a percent relative abundance of 2. If we do the same thing here, 2.4 divided by 10 times 100, you're going to get 24. 2.2 divided by 10 times 100 would be 22. And then 5.2 divided by 10 times 100 would be 52. So this is how I get from relative abundance to percent relative abundance. This is the number we need in order to go into our molar mass calculation. So let's talk about how to find the weighted mean molar mass. Weighted, meaning weighted categories, kind of like you might see some of your grades, like the test category counts more than the homework category. And then mean, basically meaning what we usually call an average, like how you would average 3 trials in a lab. And then of course, relative atomic mass is like our molar mass. But this time we're going to consider all the isotopes and we're going to consider their abundance. So if I look at the 204 isotope, we only have 2% of all of the isotopes out there, of all of the atoms out there of this, only 2% of them have a molar mass of 204. So that's going to weigh in at 0.02 of the molar mass. So basically you take your percentage, convert it back to the decimal version of the percent to get how that affects the total mass. And we're going to add our next mass, which will be the 206. How much does the 206 affect the total? 24% of it. So we're going to use the decimal version of 24, which is 0.24. That'll be how much my 206 isotope affects the total mass. Right. The next mass is 207. So that abundance was 22. So I'm going to use the 0.22, the decimal version of that percentage, to find the percent of that number. And then my last mass was 208. And that was the one that had the largest relative abundance of 52. So we're going to use 0.52 here. We're going to add up each of those. So when I find 2% of 24 by typing in 204 times the 0.02, you get, or let me do this in another color. You get 4.08 for that section. For 206, finding 24% of that is going to give you 49.44. Finding 22% of 207 is going to give you 45.54. And then finding 52% of 208 gives us our largest part of 108.16. So this was, so 4 is 2% of 204. 49 is 24% of 206. 45 is 22% of 207. And 108 is 52% of 208. So now we have 4 numbers to give us the partial masses. Then we still have to add them all up together. So 408 plus 49.44 plus 45.54 plus 108.16 gives us 207.22. Molar mass would be grams per mole. But then we do want to make sure that we follow all the directions in the question. And if you notice, they added one little extra sentence saying to round to the nearest tenth. So to convert this to our final answer, we'll go with 207.2. The 2 does not make the 2 round up. And then I'll use G MOL -1 for my final units.